about Z also. At most, you have bending about 2 axes, nothing more. Guys, phones aside, please. Thank you. This is for you guys again. MC over I about X, MC over I about Z, and at most F over A. You should not expect more terms than these 3 for sigma. In the test, I will not give you this because it's really too much work. If you're able to do these 2, as we did so far, that should be sufficient. I'm giving you one in the homework so as to sharpen your skill, and that would be it. But the test is not that hard. All right, so you have this. We developed the equation. Now we want to calculate these for A and C. So again, put some room there for M and I calculations. Repeat this for A and C. This is A, this is A, and sigma C. Again, C values get the same subscript as sigma. Again, please make sure you do pay attention so that you have easy time for the one given in the homework. Yes?
I don't want to sound stupid, but why is there 2 of the MC over I terms?
Braden, I would not call it stupid because really greatest designs came from these kinds of questions. Why not, why not, why not?
I just
creativity.
missed
You
it.
found that?
No,
Oh.
I just.
All right, so visualize this. By that force, does the system buckle about X? Buckle means like this, it's like this. You load it, it buckles like this. Does it curl around X?
No.
Look at the force. X is in the middle, this one is in the middle.
Oh. Then yeah.
Yes, all right. Visualize this, F about Z. Does it buckle about Z? Does it curl around Z?
Yeah. Oh, okay. So it buckles around 2 axes.
Yes. We always ask ourselves that question and then we find the answer to that. All right, so with that said, then we have to calculate Mx, Mz, Ix, and Iz. For the previous example, we did only 1 for each because we had only 1 buckling, but we have 2 now.
I have perhaps a dumber question.
I'm sorry?
I have perhaps a dumber question.
Go for it.
So, what letter did you write over A? Because I cannot tell if that's supposed to be L and F or P.
Which line are we referring to?
Sort of the equations. Is that force?
In here. So the thing is this. This is 6th week. We kept talking about force over area. So even if it's not readable, you know that it should be force. Right? Nothing else really gets there. So when you write it, I suggest that you write it critically. You think about it. Then that should be clear. It's not to defend myself, it's just how engineers do it. That's my point. I said it already, my handwriting is the worst. All right, so 4 volunteers, guys. For Mx, Mz, Ix, Iz. Right, these are repeated questions. Just follow the instruction and you get it there. 4 volunteers. 1, 2, 2 more. 3, 4. All right. Drew, let's go for Mx. By definition, if you have to do that, by definition, moment is product of 2 things. Force times normal or perpendicular distance. When you say Mx, You see the position of axis X, and you see the force, the distance between them. Force is given, give me the distance between them, and you get mx.
The distance would be 40 millimeters or.
That's great.
45 centimeters.
That's great. The force, so you guys, you know that, just believe in yourself. Prove a point. So mx 192 Newton meter. All right, then just so you mz, if you just give me the distance,
It would be 60 millimeters. Or 60 times 10 to the negative
again, the distance between force and z-axis.
30. Oh, 35 millimeters.
Again, force and z, not a number that you see there. Between force and z, z is in the middle. Force is 35 away from the left side. Go for it, he knows it. Think further. Stay away from Hawaii. Okay. Only he knows what I'm talking about.
Is it 60?
The
Is
z is in the middle, right?
it,
60 millimeters away from point A. Force is 35 millimeters away from point A. You see that? What's the distance between force and z? He knows that. Do not stress him out. So, look at the board.
Okay.
Suppose we're in one line. I'm 10 meters, 1 meter away from the board. You're 10 meters away from the board. What's the distance between us?
9 millimeters.
Meters. I'm giving all everything meters.
Oh, 9 meters.
9 meters, right? 9 millimeters from there to here. 9 meters, right? Do you want me to put myself there and yourself there? Look at the force, look at the board, which is point A, look at the z-axis.
Okay.
You see, the distance between z and the z-axis, f and z-axis. It is?
60 minus 35.
Yes. Which is?
25.
Right? So ask yourself this question. The distance between this and that do not fall for other numbers given.
Okay.
As engineers, you're working on a big project, let's say car, you have to collect data accordingly. Just follow the instruction between this and that. And you figure that out. Read it down? All right. All right, so this MZ then is 120 Newton meter. All right, remind me, Justin, you were next for IX?
Yep.
All right, Justin, IX,
112
yes,
base times height. One of them is cubed, the one that's
Very good.
perpendicular to the axis.
very
Which
good.
is
So
the-
now the focus is X. The base and height are the same thing, right?
Hmm.
Base and height are the same thing. Give me base and height, please.
120 times 10 to the negative third, and 80 times 10 to the negative third.
And you see that figuring out which one is base, which one is height in 3D is not a unique way, right?
Hmm.
That's why I said memorize it this way. The one the textbook said BH, one of them BHQ or BQ8, we don't know which one is B, which one is H. It matters how we define that. But if you say like that, comparing to that in 3D, it's always clear. All right, which one for IX is cubed?
80 millimeters, or 80
Very good.
times 10 to the negative third.
Justin, who was the last one raised? And who was, yes, you, Wasi, right? You were, okay, Wasi, what changes really here?
The 120 also are 10 to the negative.
Very good. 120 this time should be cubed. again, I really reiterated this over and over. If you write it down this way in your formula sheet, then it should be perfect. All right, Ix is 5.12 times 10 to the negative 6 meters to the 4, 1.15 times 10 to the negative 5 meters to the 4. All right, now we want to pick signs. 2 volunteers, please. Somebody who did not answer, please do that so that you contribute something. Challenge yourself, and only that you learn it. Okay, Ethan. One more. Somebody who did not answer. Okay, Braden. Okay, Ethan. Guys, again, the point is not to put you on the spot. The point is we're just one big team. I want to make sure that everybody just follows and learns it as everybody else. All right, so Ethan, we want to now pick out these signs correctly. So when I say this, just look at this, it means bending about x, right? Visualize the bending about x we said is buckling to the left, curling or basically flexing to the left. All right, so if it's bending to the left, look at point A. You see, point A. Look at point A. Is A being pushed or pulled?
Push.
You said that pushing is a negative or positive?
Negative.
You said that big negative. Then with that said, look at point C. Is it positive or negative?
Positive.
Positive. Great. As easy as this, guys. Ethan, a point. Braden. Now let's figure this out. These two are about Z, right? Look at Z-axis. It's bending to the left, and look at point A. Is it being pushed or pulled?
Is it not point B?
You see, we're talking about points A and C. We're interested in stress at A
Oh.
and C. And B is not applicable.
Sorry, I thought we were doing B.
All right, point A, and look at bending about Z. Bending to the left, is A being pulled or pushed? Only look at MZ.
It being pulled?
You just look here, because you're looking at yours. Just look at here, we said, if the force is slightly to the left of Z, actually by 25 millimeters, right? So that means it's bending to the left, like this. Bending to the left.
It's just being pushed.
Push. So is it positive or negative?
That would be positive.
You said push. Pulling, pushing. Which one is positive? Which one is negative?
Negative.
Negative. Pushing is negative. All right. What about point C? You get MC, MZ, but look at point C.
That's what it would be pulled?
Oh, positive, negative.
Positive.
Positive. Engineering is this. In mathematics, we never do this. Equations either given to us or we find it somewhere and then plug in values and calculate. But here we have to do a lot of analysis. That is what makes us an engineer. Braden, a point to you. All right. Now we want to calculate C values. Then we plug in things. So I want 2 more new people, please. Okay, very good. Nathan and Jesus. All right, Jesus, nothing new. Here you remember, we said when we want to solve for C or calculate C, this is the axis, right? Put these arrows perpendicular to that axis. And then you move away from that to that point. That is the length. All right? So let's get back to here. For this one, it's about x-axis. Look at point A, see A value. Look at x-axis, look at that cross-section, look at point A. So put these arrows. How far should you get away from X to get to A? You see x-axis, right?
Yes. And how far to get
You,
to?
you have to move in this direction to get to A, right?
Uh-huh.
How far should you move to get to A?
40 millimeters?
You said it, 40 millimeters. How far should you get away from that to get to C?
Would it be negative 40 millimeters?
Length.
Oh,
Length is positive. always.
positive. 40
So
millimeters.
40. So put this 40. All right, these are the points. Nathan. Now let's do this, because z-axis, and put these arrows on z. How much should you get away from z to get to A?
60 millimeters.
All right, 60. How much should you get away from z to get to C?
Also 60.
Also 60. All right, guys, be prepared for the calculations. All right, now let's put values. Let me do this in here. Nathan, point to you before I forget, Nathan Smith. All right, so negative force is given as 4.8. Area, again, the dimensions are already given in here. Mx, we found it to be 192. Ca and Ix 5.12. And Mz 120. 60, and Iz is 1.12, 15 counted -5. In fact, these are the same, just the signs in between change. So take advantage of that. And Jesus practiced on this the way that we just did together.
Mhm.
And let me give these values to you. Again, guys, let's keep trust each other. Do the work, learn it. If not, resolve the issue with my help. Get the bonus point and get better at it.
That's too.
Because these are longer calculations, I'll give you a point for each. But just make sure you do both. You do both, then raise your hand. Are you doing both? If you did both, I mean it, okay? Drew 2 points, Evan 2 points. Guys, let me emphasize, because I've seen some, unfortunately, people falling for Satan's trick. Please do not do that. Do the work and get the points. Evan, I think I did just give you the point. Okay. Jacob, those are all 2 points. Justin, I saw you. Josiah. Bossy. Only through practice you get better. If you have a private tutor, this kind of interaction only happens there. And think about it, I'm handling about 30 of you in each class. I'm doing this with each and every one. So I'm really doing my best. Please take advantage of that. If you're done, take a break now. Please come back by 11:28. The efficient way to do it is really do one ratio at a time. Calculate it, store it, and then move on to the next ratio. Calculate it, store it, go to the third one. Calculate, store it, and then set the three up. You do both? Actually, that's why. All right, so let's first let's confirm that. Then, because you already assigned this value, just you see. Or the
I'm doing
first
step
was
by step.
negative.
The first one. This is what you
First
guys
was
do.
negative.
Yes.
So that should change.
Awesome.
and then-
It's negative though.
Here, just-
Well, it's
I
like
believe
negative.
If you say so.
It's the same guy, it's negative. Just don't forget that negative.
I don't care. Like that's,
And then
You don't
when I
get-
say mega.
Well, no,
divided
you get
by
negative.
6.
Because there's just a minus on it.
Got
You
it.
know it's not.
Got it.
Because the force is going down, so we can assume it's negative.
Now it's good.
So your value's right.
That's fine.
okay.
It's not a calculation.
I believe you if you say you did both. I didn't ask you. No, did you do? Just confirm. Just say yes, I believe it.
129 times 40 squared.
I confirm and say it.
Negative 3.
That's
129
okay.
times
Points
40.
to get. Yes, you say you did. I don't have to see it. Yeah, just confirm. Decrease, right? Yeah. Two points to you. That was the idea. Just make sure once you found the force value, make sure you determine whether it's tension or compression. If it's tension, then pick strength and tension, otherwise pick the one in compression.
Yeah, that's where I ended up messing up.
You fix it. You're fine. You just confirm. So you're copying and pasting, right? You're just changing the sign. How do you get from that? That's right. Positive value. Oh, no. Positive, you see, this is still negative, this is what I'm saying. Positive only for the next two.
Yeah, so see how these are negative,
Yeah.
there's a negative 1.6, and if I put the negative sign in front of it like I was supposed to, right?
Yeah.
If I did that, then it gives me a different value. I don't know why.
Just you see, you're doing this last one, right? The second
No,
one.
I'm trying to do the first one.
The first one again.
Both ones are negative.
I see.
Yeah, I'll take a look at it, I'm gonna,
that.
Oh,
Top one I get is
Enter, it shows
7.2 over an ass. You have your mic up a little?
it's not.
So we expect this value to be this.
She probably said this word. If you go about 4 years.
Like 2 digits.
You mentioned that.
Yeah, 2 digits.
It just needs to be
Yeah, I guess,
and you can
But you-
put the second one also.
Yeah, that's.
All right, Ethan.
thank you.
You confirm that one? Yes? No, I trust you, if you just raise your hand to say confirm, I'll give you the points. How to do that? All right, so the idea is this, suppose you did the big calculation, and then something like this, and then you came up with this number, right? What do you do
Is it
with
supposed to
this?
be negative?
Again, suppose this came from a big calculation. You just took store, you see, hit that, and then pick the letter A, B, C, D, you see. Pick A, for instance, like that, hit enter. From this point on, A will be that message. And then you do another one on B, and then do another one on C, and do A plus B plus C. Right, A plus A, B, something like that, if you define B already, but B now, so it takes B as
This is
not just the second and the
You
third.
did the first one, right?
Yeah. The first one.
I get 5. 5 to the 10. 5.
So I got
Olivia, are you confirmed for?
Yeah.
5 times 10 to the fifth was subtracted by 3.7 times 10 to the seventh.
Never mind, I fucked that shit up. I'm gonna go back.
If this means anything, we're not going to both of them up.
Neo.
So it's got to be something.
Neo.
Are you? Just solve the numerator, solve the denominator, and just plug them both in. And I like to put parentheses on the denominator just to make sure that there's no way it messes up. Because sometimes a calculator doesn't
For
do
the,
what you want.
Anything you want to watch
These two
already,
parts.
scroll eyes. If it
7.68.
becomes like this, just watch it, just spin it for you. You good?
192 times 40 to the 10 to the negative third is 7.68, right?
Yeah. Okay. I didn't write it down.
Oh, okay. Then I divide that by the bottom. So 7.68 divided by 5.12, 10 to the 6, negative 6. Right?
What's your number, bro?
It's supposed to be that, right?
It's pretty good.
Unless I did the 100 and, it's 192.
So this should be 192.
Yeah, 192 times 40, 10 to the negative third.
I get 76.
Yeah, that's how to get to.
Okay. And then I take that number.
And you divide by 5.12.
What do you get?
I get 1.5 e to the 6.
That is not on the side.
Alright,
But let me double check.
I could be typing the numbers wrong. So don't worry. Scientific.
Oh wait, no, that is. Yeah, it sounds too. But that's what I got.
What? So, okay, delete that one.
So Jesus, Braden,
Huh?
are you good? So one ratio at a time.
Yeah, we're doing one ratio at a time.
Yeah, so
And
Did you figure it out?
I'm double checking my math with him.
But overall, you have the value there, you see?
Yeah, I have the value. I'm comparing the numbers to get to the value.
But do you happen to confirm any of those yet?
We confirmed that these two are right. Then we're working on this one.
The next one is just the same thing, A, B, C, you call them, right?
Yeah.
So A minus B minus, A plus B plus C this time. So it depends on what signs you picked.
Okay. What?
You did not?
No, I'm just looking at this. I put in, I was trying to go through this again. And I did my answer divided by this without a parenthesis, and I get a -6.
Yeah, so that's the issue. This is the part I said you have to know your calculator. This one is correct. Because it's small number in the denominator should really get bigger. So that means from this point on, you have to put parentheses in your calculator. Mine does not do that.
Yeah, or something to do, because it's probably taking.
E value seems if you put, then
Yeah, it's taking and just putting in that and then multiplying by 10 to the 6, and that's why it's negative.
Yeah, got it, yeah. But yeah, I think some people said in their calculator, if they use the letter E instead of 10,
Yeah.
it seems that it works properly.
Okay, I'll try and do that
Yeah.
more.
You see, that's why I say,
Yeah,
do
know
that
your
in class,
calculator.
yeah, know your calculator. All right. Guys, let me throw out a big word that even the pronunciation is hard. Phenomenological modeling. Guys, phones aside, I gave you the break. This is for you guys now. Phenomenological modeling. What is that? So it's something that has shown up in my research. And since I learned that, I was able to relate to it and then talk with my students that way. So when I was teaching heat transfer elsewhere, there were so many big equations, let's say 3 or more, at least 2 equations for calculating one particular parameter in heat transfer again. But the 2 or 3 would not always be the same values. And students always ask, which equation should we use? Why different equations? Why different values? It doesn't make sense. It doesn't make sense. I agree. So when I was talking with my colleagues, and I think they were not able to come up with a good response to that. So I think I came up with something good because students really liked it after. So the idea is this, phenomenological modeling. What is that? So we talked about Hooke's law, right? Open question. What is Hooke's law? Raise your hand. Josiah?
Sigma equals epsilon times E.
Very good. Sigma equals E epsilon. And we said it's not a law because it's not always correct. It's only correct in the elastic region, right? We said in the elastic region, like this. In this very region, elastic region, sigma equals E epsilon. This is sigma, this is epsilon. Sigma equals E epsilon works. And even in that region, if you zoom in on that region, that line is really not a line. It's really a combination of scattered data points. What people call it a law, it's a misnomer. So how those people came up, or let's say the Hooke himself, how did he come up with this equation? He said, look at the data, I see that it's mostly linear. So I draw a line there, I come up with that slope, tangent of theta, let me call it E, the stiffness. And he said, okay, sigma equals E epsilon now is the equation. Instead of communicating all the data points, he says only communicate the E value for all of the points. So this kind of modeling, by just picking an equation by looking at the data, and then coming up with the constants that show up there, is called phenomenological modeling. Yes, it makes it easy, makes it really easy, but some issues, there's no physics behind it. It's only specific to that region. And another big issue is this. I may come up with one particular equation, you may come up with another equation. For linear, yes, it's easy to say it's really a line, but something that is like this. What equation do you want to go for? Sinusoidal, exponential, sinusoidal. You see different forms could show up there. And heat transfer, when you take it, you see that big equations, and the instructor is not able to comment on it. He cannot say where that equation came from. But you guys should know that. It comes from phenomenological modeling. Now, different equations, different accuracies, even the region that they're really talking about. So in this course, some of the equations like sigma equals epsilon, or the deformation for thermal behavior, delta T was alpha L delta T, right? So that one came from phenomenological modeling. I simply said it came from physics, but in physics they really came up with this kind of modeling. But they do not use this word. It makes it hard to really talking about why. But if you know this kind of modeling, you're just familiar with the concept, that's sufficient. So that's something I want to share with you. Now, with that said, we want to go over the last theory slide for this leg, for chapters 4 through 6. And that's this. So it turns out that when you apply moment to cantilever or force, two things occur. One is sigma, normal stress, the other one is shear stress, tau. So in test, I might ask you for the stress, the equation for normal stress due to bending. This is the one that you already learned, you practiced a lot, MC over I. When there is bending, shear stress also occurs. All right, so let's go over the equations. Again, I'm giving all of the equations collected from the textbook in one slide for shear due to bending. So there are two equations for this. First of all, let's go over the theory. So suppose I apply this load, this force at the endpoint. It bends downward. But why does shear stress occur at all? So suppose the cantilever is composed of layers like this that you see on top of each other. So this top, as you apply the load, this top layer slides over the one underneath. And because of this slippage, shear stress develops. Whenever there is shear, there is shear stress. All right, and look at this case. We have 3-point bending. And look at the failure. The failure is not snapping anymore. It is horizontal opening. So wood, in particular, is susceptible to shear. They're weaker in shear. Do not use them if you think you're pushing them like this. They open up. Use another material. All right, so that's the lesson out of this, but how do we model it? In two ways, giving the same result. This is BQ over IT is for general geometries. No matter what the cross section is, that always works. This is special. It works only if the cross section is rectangular. In this case, the textbook gave us this trapezoidal shape. So this lower one does not work. Now, I do not want you to memorize this one. We do not care about what happens in between. So instead, if I say what is max shear stress equation, For rectangular geometry, you just give it a coefficient, 3/2 B over A. What does that mean? So if you look at the stress profile from the side, if you look at from the side like this, so it turns out that the shear stress is 0 on the extreme sides, on the top and bottom, but it's max on the center. But for normal stress, we already went over that. It was max. If you push it downward, we have sigma max on top, and negative sigma max, and then we had 0 on the neutral axis. So really, sigma and tau are complementing each other. If one is 0, the other one is max, magnitude-wise. Guys, please pay attention here. Guys, you open up the laptop and you're looking at something else. Please pay attention here. Sigma is max, tau is 0. If tau is max, sigma is 0. The two complement each other, magnitude-wise. So sigma and tau complement each other magnitude-wise. That means if one is 0, the other one could be plus or minus sigma max. Whether it's minus or positive, you have to do the usual analysis. This, you're pushing down on it, it bends downward, the top face is positive, the bottom face is negative. This is something that we already went over. Alright, so this one is easy, 3/2 B over A. And you remember for joints, in chapters 1 through 3, in leg 1, for test 1, if you have two plates, if we connect them with a pin, tau was B over area, or we said F over area parallel, B over A, but look at the one in bending. There is a coefficient other than 1.5. All right, so now, this is for rectangles. So we said it's max here, it's 0 here. It's not linear anymore because of the presence of this square term. It's parabolic shape. All right, what else? For general formulation, if it's non-rectangular, we have to use this formula, BQ over IT. I is the one that we already learned. So this text box, we already repeated that in sigma calculation also. T is the thickness at the point of interest. I'm going to give you examples as usual. Q is this big term. It's best to go over examples to show you how to calculate it. If cross-section is rectangular, it's best to use the second formula, it's just easier. If it's non-rectangular, you have to go with general one. So let's do the first example. If you do this, then you're equipped with equation to do all of the problems of the homework that I posted. So this is that diving board example, for instance. So given this cantilever and dimensions and the force, we want to calculate shear and normal stresses. Calculation of normal stress is nothing new, we already did. I just want to do them side by side as another example. I'll give you time. So let me confirm Paul Arden is absent, AJ is absent, and everybody else present.
Yes. Could you zoom in on the picture, please? Thank you.
So maybe next class, by next class I post the project document. So there's no final exam, instead you do the final project in teams. So I'll post it next class, and then you have almost half the term to finish that as a team. Basically you'd be, Josiah, good? Basically, you'll be picking or choosing a bridge, and then you'll be analyzing it. You'll be looking at the top face of the bridge, you'll be looking at the middle and the bottom face. You'll be calculating stresses on those points along the length of the bridge, and then given the material property of the concrete, that you'll be finding through your research, whether you contact the company who built it, or certain thing that I'll go over next class, will be basically commenting on the safety of the bridge. If it failed, your calculation basically should show that. So that will be our project. So that's why here we're focusing on those 3 points. Really, those are the critical points. Those are the points that either sigma or shear stress are maximum magnitude-wise. All right, so we learned, open question, let's review quickly. Which points we know that shear stresses are 0? 0. Where else? A. We said top and bottom faces. So conceptually, why is that the case? We said it's about slippage, right? So if you look at the top and bottom faces, there is no further layer on top or below these 2 layers so that they slip over. For that reason, shear stresses are 0 there. So tau A, tau C are zeros, greater than 0 each point. And at which points, normal stress is 0. B, very good. At which point shear stress is maximum? These bonuses, guys. B. And at which point sigma is maximum?
A and C.
A is, which one is positive? You tell me which one is positive in this case, which one is negative?
A would be positive, B would be negative.
Very good. Jacob, Justin. So sigma A is sigma max, and sigma C in this case is negative sigma max because of symmetry. Point C gets pushed or shortened. That face on the bottom gets shortened or wrinkled. So really we need to calculate 2 things. Tau B, which is tau max, through 2 formulae, which means the plural of formula. All right, and then this one, we just care about calculating one value, sigma A. So, for tau, we said there are two formulae. One is special, which is 3/2 V over A, for rectangle, because indeed it is rectangular. The other one is general VQ over IT. That's general, it works for whatever geometry, including rectangular. So why bother to really learn that? Because some geometries we have to use that for, and in particular the next problem. All right, the first one is easy, 3/2. V is the force that is literally given as 10 kilonewton, 10 times 10 to the 3, 10 to the 3 for kilo. And area is cross-sectional area, B times H. So 5 centi, 10 to negative 2, and H is 25 times 10 to negative 2. So 1.2 megapascal. The next one should give us the same value, but with more work. Now, V as before is 10, I, we're bending about this. For sigma, I need to do the instruction. Put the coordinate system at the centroid of interest, which would be like this. If I go X, Y, Z, Z is not drawn well, it's like this. So we see that it's curling around which axis, guys? The bending is about which axis? True?
X.
X. Very good. Bending downward about X. So real I is I about X. We know that this is MC over I. M and I get the same subscript. So really ask yourself this question all the time. It's bending, curls around which axis? So something like this specifically has been part of the test before. All right, true R equal to you. All right, IX, there's nothing new. Open question, how do you calculate IX? Maybe Jacob was slightly faster.
For the IX, that is 1/12.
So how will I do IX here, because we're going to need it in here too?
Yeah.
So go for it, please.
1/12
Yes.
base times height, and then 1/1 is cubed.
Which one cube?
Perpendicular to our x should be our h.
Very good.
Yeah.
6.51 times 10 to the negative 5. All right. And check it. So let's put that one in there. All right. T values, the thickness at the point of interest, and T goes for TB and Q also QB. All right. TB is the thickness at the point of interest. It is B. 5 times 10 to the negative 2. All right, now QB calculation. That's the one that is normally catchy. So look at that. Look at this. AY times Y part. So what is that? Let me zoom in on the cross section. Point B is somewhere here in the middle. So this is half H. And this is B. So please, can I have your attention? This is important. If you do not pay attention to this, the text may not be explained this clearly. So look at this. I'm interested in calculating Q for point B. Look at the cross section. Go either top part or bottom part, doesn't matter. Pick one, stay with that. This is symmetric in this case, it gives you no preference. Well, let's go the top one. The area is that this dashed area. So B times H halves. So let's actually add one more term here. We said A, B times Y bar. We paired the equation. A, B is B, H halves. That's A. And what is Y bar B? Let me switch to blue. What's this? Look at the centroid of this. This length is Y bar B. And we know that in this case is H divided by 4. So a quarter of H. So the distance between the centroid and the bending axis is, from the point is H4 in this case. So that is Q value. You see that that's really involved compared to the first formula. So let you put the values then. B is 5 times 10 to negative 2. H half is 1.5. And H4 is 6.25. All of this is our Q value. If you run this, you should get the same thing. So I see some of you are calculating, and I'll reward you for that. Once you did both, raise your hand, I'll give you a point. Dylan Sturdy, can I help you with this?
You mean getting both for just shear?
It will be the same for both, right?
Right.
Just confirm.
Oh, yeah.
Confirm both. You did?
Yeah.
The second one is longer, so at least confirm the second one. The both should give you the same. Through practice, you only get better. You only get better. Audrey, Leon, Justin, Jansen, Wasi. Why, do you see how quickly I learn all of the names? Yes? Reagan, did you raise your hand too? Great. Fighter. Hero. Evan. It must be error. Assuming that was correct. That's the value you found, right? If you convert it to mega, it becomes that. Doesn't matter. You didn't convert to mega. You were waiting to say. giving you up to 1%. You're looking at 5, 6, 7 digits. You see this 120, where is this coming from? This is 12.1. That's one, and then, let me see. Yeah, hit enter. Yeah, just change that to 120 to 12.5 and see, and then divide by 10 to second, you get an account. Packs, Australia, Ada, thanks for doing that. Please do that more.
The other two, I was putting in the calculator wrong, so I just figured out what I was doing wrong.
You figured it out
Yeah.
eventually, but confirm that. Which ones you did? These ones or previous ones?
The previous ones I was doing wrong.
But you never fixed them?
I fixed it.
Now let me, so I give the point. So remind me, these two you fixed?
Yeah.
All right, we had 2 points for those. You fixed both. All right, give you and give you 2 points. 2 more points for those. All right, yes, we fixed that. Oh, you're missing 10 to negative 2. You see that was 12.5 times 10 to negative 2. Yeah. Oh, I see what you did. You had done 12 times 10 accuracy. You see this is 12.5 times 10 to negative 2. You need that 5 around there and it gets you there. All right, Olivia,
1.25.
Gabe,
So that's 1.25 pascals. So you
Ethan,
divide it by 10 to the 6th,
Drew,
which is just.
Nick Reese, thanks also for doing that.
Yeah.
Jack Fedul.
No.
Is it
it's
Fedul or
it's in
Fedul?
Scientific method, that's what it is.
Which one? The second one,
That's gonna be a
Fedul?
negative.
Yes.
This one works.
Smith.
This one was easier than
Jesus.
the other ones. I don't know.
So for
Alright,
this one,
very
it's
good.
just if we solve it like this. It's
All right, so let's do
perfect
this
rectangle,
one.
right? Then this one's if it's not.
But they're
So
supposed to give you the
MX
same answer no matter what.
Yeah.
We know that it's the moment of the force. So force times L, because point B is here and that's L. So force is given as 10 kilo and length is 1, that's moment. And C value is the C of point A. Again, we go perpendicular direction like this, go away from that to A, and it is half of H. So CA is half of H. So 12.5. 12.5 2, and I is the one that we already calculated. So this one is 19.2. Again, this is a repeated calculation because we've done even way more work, way harder than this simple example for normal stress calculation due to bending. But this is just simply to put it on perspective and compare side by side. So suppose sigma ut is 25 megapascal. Suppose sigma u c is 15 megapascal, and suppose tau u it's 2 megapascal. Then in the interest of time, let me do this myself. We see that sigma u comma t means strength in tension, and this is positive, so compare with this for A. So that is greater than 19.2, so A is safe. Sigma UC would be for negative, and C would be the point of interest in this case. So because this is less than 19.2 that we're giving it to, so this 15 is not good enough, therefore C is not safe. And tau U is the shear strength. We have to be looking at point B, because this is greater than 1.2 for B, so B is safe. So, but one failure too many. So overall not safe. Remember, if I just give you sigma u value and I do not define comma t or comma c, that means they're the same in tension or compression.
How come compared to the last problem, we didn't do force over area plus or minus the 19.2 megapascals?
Anyone can answer that? So Justin is asking a valid question. He's asking why don't we put F over A in here? Yes,
Is that because the points are fixed to the wall?
even there it was fixed. Was,
I think Drew had a second.
oh, Drew, okay, go for it. Thanks for,
So, which to add on to that explanation, there is no displacement across, across the material.
thank you. So see that? When we put the instruction here, develop stress equation, enumerate axial bending effects. Are we actually applying any load? No, it's just bending. It's all about bending, as Bruce said. Wasi, what did you want to say? Because we're at the same time.
I was gonna say force was not on.
Basically, did you want to say the same thing or a different thing?
I'm assuming the same thing.
Or then say it because you're not sure to say it.
The force didn't seem like it was perpendicular to the actual object was to the side. That was my explanation.
So that was bending. You're talking about bending. The force causes bending, but really the point it was what Bruce said specifically. The force is not creating a pulling or pushing effect. That's why we do not put any force over area. That one from top only creates bending. Let me go back there. This one creates only bending. We do not put F over area of that at all, because that's not really force. Because if it were fixed from underneath, if we load it like this, yes, it would all be F over area also included. But it's open to move downward, so really it's not axial loading. All right, if no more question, let's see how much of this we can get. Maybe I can do this faster. I'll let you write this down. Suppose we go to Home Depot, Menards, where else? Lowe's. We purchase 3 lumbers of those dimensions as given. Write the statement down, please, and I'll zoom in on the figure. The problem is from textbook, but it's a lot of simplification. Remember, when we calculated I for T-shape, it was very involved. By giving that I calculation here, so that we'll have only engineering discussion rather than mathematical complexities. So suppose you put those 3 lumbers on top of each other and you create this I-shaped geometry on the cross section. And then you suppose you glue them right here and here. You want to calculate the stress there at those 2 points. And if we know the glue's, let's say, property, then you can determine or figure out whether the glue is safe or not. For joints, we normally care about shear stress type, because they're susceptible to slippage. They will be cut. They will not snap. So really shear stress is the key calculation here. That's why it said find shear stresses. We have about 11 minutes. And guys, if you want to me zoom, just quickly take pictures so that I zoom back and start writing on it. Figure. Because it's not symmetric, look at the upper piece and the bottom piece. Because they're not symmetric, the central is not exactly midway of the total height. And we calculated centroids in statics, and also we reviewed in this course when we looked at the T-shaped cross-sectional geometry. And we did about 10 calculations for I. All right, so I want to finish this up. So we want to calculate tau at A and tau at B. So first, special formula, tau max equals 3/2 mu over A, not applicable. Even though the three ingredients are rectangular, the overall cross-section is not rectangular. So we have to resort to VQ over IT. So Q gets A, thickness gets the subscript A. In the same way, B. Remember, for bending, with these three axes, it curves around this axis. What do I label it to? So suppose X, Y, Z. This time this I is about Z. So I is about Z really. If I give you I about other axes, you have to pick the right one. And in this case, it's Z. All right. Three of them are easy to calculate. Only the Q part is, let's say, demanding. V is the force, is given as 1.5 kilo. You have that. Let's do in parallel. IZ literally given to us. Again, you're welcome to take a look at the textbook. Makes it all that work. Really, with no engineering discussion or advantage. All right, thickness at point A and thickness at point B, really they're the same, the thickness of this middle piece, or really the glued area, they're 20 millimeters, up there, 20 millimeters, the media is 10 to negative 3. Now for Q, QA, we know that it is area A times Y bar A, and QB, we know that is area B times Y bar B. So let me zoom in on the cross section here with my, as usual, great handwriting that Nathan does not write much. So this is the zoomed in view. The centroid is here C. Dimensions are given better on the figure itself. So let me switch to another color, maybe blue. So we said if you're interested in this point, A what do? Go either top or bottom. If I go top, I'll be looking at only this cross section. If I go below, then I have to really go for these two segments. It's much harder. So go for the top. Eventually, I guess the same thing. So the area of this by inspection is 20 by 100. So put that in here, 20 by 100. 20, not 200. All right, that's area of that. Y bar A, let me switch to yellow. So the central is here, that's the length. Yellow is not good enough. Maybe purple, no. Green, this is this. And then the central. By inspection, we have to really figure out this length. We know that this little thing is middle is 10 millimeters. We know that all of this is 100, and from here to here is 100 minus 68.3. Is this little 10 added to that? It gets 41.7. So QA, if you multiply these numbers, you get 8.34 times 10 to negative 5. You have about 5 more minutes. For the bottom one, you do the same thing. The point of interest is here. You go either up or bottom. If you go up, then two pieces are involved. It's much work to do, yes?
So for A, wouldn't that be an overall length of 120, not 100? 20 plus 20 plus 80?
So there are different ways, right? Just, I'm interested in the length from C to the midpoint of that, right? So what I did, one way is to look at this entire length from this bottom face to this face. It's 100, but I needed this length from here to here, and then this little. Right? All right, for the bottom one, for point B, do the same thing. It makes sense to go for the bottom area, it's just easier. And it is 60 by 20. So that's area. And what we care about for Y bar B, it just, again, the middle here to here. The entire thing is 68.3, and this little thing is 10 millimeters. So 68.3 minus 10, 58.3. And this is 6.996 times 10 to negative 5. So meter cubed is the unit for Q. In this course, we've had different units: meter squared for area, meter cubed for Q, and meter to the fourth for J and I. All right, basically we're done, but if you have these values with you, if you confirm that, let me know so that I give you the points. Guys, again, do not corrupt our trust. Do the work if you want to deserve the point. Again, if I suppose the glue that you bought from that shop or store, it has the strength of, let's say, 1 megapascal, then both A and B are safe. The strength should be more than the stresses that you're calculating. Instead, you did the calculations so quick and precise. make sure you go over homework. If you need my help, please show up in my office hours on Thursday. Drew, I didn't understand. Will you confirm me?
Yes.
You did do that early on, but I gave so many points, I'm not sure. Did I give you the point? You just did? All right, let's, Ethan.